All right, so today we're going to be coding out Dijkstra's algorithm, and to do that we're going to look a little bit, just take a peek at some graph networks. I'm going to go ahead and ping some people in my Slack channels. So just one sec. All right. So I'm just gonna double check my mic really quick. Might turn my mic up just a little bit. So a little quiet. Well, no, that's not too bad. Okay. Maybe I'll see if I can make it a little bit better. All right, all right, all right. Hello, hello. Maybe a little more. Hello. Might be a little too hot. There we go. I think that's about where it should be. Cool. Okay, so today I'm going to be coding out a simple graph network, and from that I'm going to deploy Dijkstra's algorithm across all the nodes so that every node has a cost table, and from that we should be able to get a lowest cost path. So I'm going to demonstrate that a little bit. I'm not going to heavily dig into the algorithm. I'm just sort of going to talk through it as I code it. And I'm also going to create a quick repo. So as you can see, I've got GitHub up, and I'm naming the repository Dijkstra's algorithm in Python. And if you notice what I'm doing here, I selected public, I initialized it with a README, and I added a git ignore for Python. Probably not necessary, but I did it anyway. That's what I usually do. And yeah, I'm just going to create this repository. And wait for it to be created. And okay, and then I'm just going to clone it down. So I'm going to grab this, and over here git clone, and this is going to pull this down, and that's the folder I'm going to be working in. So notice if I type ls, I see the files that we would expect to see here. So before I get too far into this, I'm going to, well, let me think about this. I'm just going to point you at a couple resources. So the version of Dijkstra's, not that there's all that many versions, but the version of Dijkstra's that I'm using is from this video that I link to in the description, and I'll also put it in the chat. And this is a really nice sort of, walks you through what the cost table is. They use vertex, I use the term node, but it's kind of all the same thing. And this is from the computer science channel. So there's that. And there's also this video, which I think is pretty good. on Dijkstra's algorithm from Computerphile, so I'll throw that in the chat as well. All right, so I'll kind of leave this repo up, and I'll reload it as we go forward. So the first thing I'm going to do is, well, I'll just talk a little bit about the process I'm going to use. So the first thing I'm going to do is kind of draw a graph and talk a little bit about graphs. And then I'm going to write a graph class in Python. And kind of concurrently, I'm going to write a node class. So kind of in preparation for that, I'm going to go ahead and make a file here. So I'll just call this dijkstras.py, and I'll open that. Actually, let me do this. Oh, I know. I'll just do this. All right. So this is just opening up VS Code. I'm going to do everything in VS Code, and I'll be running in the terminal. All right. So I'll be primarily working with this one file, dijkstras.py. I'm going to build my classes within this file, and that will be, we'll go ahead and run that. So we'll run that in the terminal. Let me just get this set up in a way that is nice and viewable for people watching. And yeah, I'll give just a little more real estate here. Maybe I'll go to there. And I'll move my terminal over just a little bit, say to there, and I might back this off a little bit. Yeah, that works. All right, so there we go. I think that works. All right, so yeah, let's look at a graph, and I'm actually going to write a graph, and we'll use this as our as a graph that we'll build in code. And I'm going to try to make this pretty flexible, so we'll just take a look at that as it comes together. So got a piece of paper here, and I'm going to go ahead and start drawing something. All right. So graphs have nodes and vertices, essentially. And I'm going to make a node called A, and B, C, D, E, F, G, and H. And all of these, we can think about them as locations. We could think about them as different cities. That would be fine. We could think about them as shipping locations. There's any number of ways to think about these. And I'm going to go ahead and connect these in certain ways. So I'm not going to connect every node to every node, but I'm going to connect these in a way where we can start looking at the paths between things in this network. So this seems pretty straightforward, right? You might be looking at this and saying, oh, well, you know, the fastest way from A to H is going to pass through 2 other nodes, and that would be correct. So one of the things we want to consider is the actual cost of these vertices. And cost can mean any number of things. It can be, it could be literally a distance, but more often it's meant to represent something like, you know, time or financial cost, you know, something to that effect. So, you know, we can imagine that, let's say these are different bike paths, and you know, you're planning on, you know, riding between a couple of different points, and different bike paths have, you know, are easier than other bike paths, and maybe there's the labor of going up and down hills or something like that. Let's see, 2, 6. Let's do 5 up here. 7, 3, and 6. So to kind of give some clarification here, what we're getting at is that if you're going to travel from A to, let's say, F, the cost of that, if you travel through C, is going to be 12, right? 7 plus 5. If you're going to travel to F via D and G, then it's going to be 2 plus 6, 8 plus 7, so 15 if you were to go this path. If you're going to go to H, you know, with this roundabout way, 5 plus 4 is 9, 11, 14. That would be the cost to go this way. So you can start imagining there's going to be some lowest cost, and you know, if you just take a quick look at this, you can see if you're traveling from A to H, the lowest cost is going to be via D and G, and that cost would be 11, 2, 6, 3, so 11. We can approach solving this in a kind of systematic way. It looks like my mic is overdriving just a little bit. Yeah, so we can approach solving this in a fairly systematic way. And if we think about the home node or vertex as being the initial thing we look at, we can imagine we visit this and we look for the lowest cost, and we, you know, go to the lowest cost neighbor, which is D, and then we might consider where we can connect to from D, which would be C, G, and E, and we might start considering, you know, what is the lowest cost at that point, right? And then, you know, C might be the next thing we consider, and we might look at the previous node D and set that in a table so that we're always kind of looking backward. So, you know, we might go to C, and then from C, the only one that we're really considering, I mean, we can look at these other costs, right? Everything that C is connected to, you know, connected here, and we can start, you know, creating these, you know, stepwise estimates of the cost as we build out the graph. And with Dijkstra is actually going to get us this least cost path. And, you know, we're doing this with just a handful of nodes, you know, 8 nodes, but we could do 100 nodes, and we should be able to apply Dijkstra's in a reasonable way, in a reasonable time. And I'm not going to go too into Dijkstra's, but I am going to code it out. So my hope is that you'll see Dijkstra's algorithm through the lens of the code. And yeah, we'll go from there. All right. So that's the graph we're going to be building, and I'll just start, representing this graph in Python. All right, let me pull up VS Code, and yeah, so if you followed along with my SIR video, I think in that I used an if main block, and I'm going to go ahead and do that again here. That's, it's a convenience. I find it to be convenient. It's like saying, this is the procedural code that's going to run, and I'm going to put all my functions, and in this case, I'm going to put classes above my if main block. So all this is saying is, when I run this Python file, this is going to be the code that's executed. So the first thing I'm going to do is define my nodes, and maybe I can pull up a little snapshot of that graph just so we have it somewhere. And I'm going to put this just up here for the moment. So the way I'm going to define these, and this might come back to haunt me a little bit, but I'm going to define these with dictionaries, sort of. I'm actually going to write a node class, and the way that I'm going to kind of define the node is that there is a name for the node, which I'm going to generally call node name, and that's going to be the first thing that the first parameter for the initialization of a node. I'm just going to name A. This is the variable, but I'm going to go ahead and name it A. I could name this Boston or Calcutta or something, but I'm going to go ahead and name it the actual letter value. And if we have a little time at the end, or if you feel inclined on your own, you can take the code that I write and adapt it, just put in actual names of places and something like real costs, and you should be able to get a least cost out of this. So the second thing I'm going to pass in is a dictionary of the connections. And if you look at the connections from A, we've got a connection to B, and that has a weight of 5 or a cost of 5. We have a connection to C that has a cost of 7, and we have a connection to D which has a cost of 2. Now, if I run this right now, we don't actually have a thing called a node, so we're going to have to start writing that. And the way that I'm going to write that, I'm going to start this off very simply, and then I'm going to start building it out. So this is just going to be class node, and I'll give myself a little space here to work with. I'm going to say class node, and we're going to initialize this node. I'm going to say def init, and when you write a Python class, you always sort of have, you have this init method of the class, and you're going to pass in your initialization arguments, right? And in this case, it's just going to be two things. It's going to be, so you also put a self-reference, right? For any method in a class, you put a self-reference, and I'm going to pass in the name, which for this node is going to be A, and I'm going to pass in the dictionary of the connections. And what I'm going to do with that is create a couple class variables. I'm going to say self.nodename is going to get that node name, and self.connections is going to get that connections dictionary. The other thing I'm going to make is something called a cost table. And this cost table is going to have the cost from a given node to every other node. and it's also going to have the previous node for that cost. And instead of explaining it, I'll code this out really quick, and I'll write a quick what's called a dunder repr, dunder repr and a dunder string method, and we'll take a look at what those look like. This is dunder init. Dunder just means double underline. So I'm going to say that we have this cost table, and this is going to be a dictionary, and it's going to be a little, I don't want to say ugly, but it's going to be, the node name, which is passed in. I could have used self.nodename there, but that's okay, I don't need to. And node name is going to refer to another dictionary. That's the key for the dictionary that contain a very small dictionary, contains two items, the cost and the previous node. I'm just going to call it previous. And with this initial one, for this initial one, we're only considering, this is the node itself, so A. The cost to go from A to A is 0, right? And there's no previous node. So that makes sense, right? We're not worried about the cost to go from a node to itself. So we're going to go ahead and do that. And then we're going to also initialize this cost table with a couple more values. And those are going to be from the connections. So I'm going to say for node name, I'm going to use this variable a lot, and just consider what it's referring to. So for each node name and cost in self.connections.items, so I'm going to traverse this connections dictionary, right? Or actually, this connections dictionary. And maybe what I should do here is throw a self in front of that if I'm going to be consistent. Let's see. Once I'm in there, I'm going to update, or I'm going to add some values into the cost table. I'm going to add 2 values in. And this is sort of a bad practice that I'm committing here. So I'm just going to change this to name, not node name, because we already have a node name, and I probably shouldn't use the parameter name within this for loop, even if it is going to be destroyed once the for loop ends. So self.cost table subname. So for each node name, I'm going to make, I'm going to add in the cost. So for each connection, I'm going to build this dictionary. And given that these are the connections from A, and we're trying to figure out the distances from A to other nodes, it makes sense to have the previous for these connections be A, right? And we can see that up in the upper left in that graph, right? C, D, and B have a previous node of A. So that's pretty understandable. Now I'm going to do something that, even if you've written a few classes here and there, you might not be very familiar with. I'm going to write a repr function, and so a dunder repr function, and this is going to allow me to print a node in a way that's meaningful. And maybe I should just demonstrate why I'm doing this. Let me just demonstrate that really quick. So I've got A down here, and I'm going to go ahead and print A. And I'm going to go ahead and run that. So Python, Dijkstra's, and syntax error. Okay. When I build this node, I did not use a colon. So that was my connections dictionary. I was missing a colon. notice that I get this not very meaningful thing that says dunder main.node object at memory address. So I'm going to go ahead and make something that's a little more readable. I think that'd be nice. And I'm also going to commit this. So add that and make a message that says, create node class. And I'm going to push that. And if you want to grab code as I'm working on this from the repo, I'll go ahead and paste that in the chat. I think it should be also in the description, but just in case, I'm going to put it there. Okay. Cool. And I'll do my best to commit fairly often and in meaningful ways, so that if you want to go back and look at my commit history in that repo, you should be able to kind of recreate what I've done here. All right. So I'm going to use this dunder repr, and I'm going to create also a dunder str method, and they're going to basically look the same. So I'm going to create a, well, first, this is mainly to facilitate outputting the cost table. That's really what I want to do here. So I'm going to create a header for the cost table, and let's make this tabbed, and it'll be node cost and previous. And I'm going to go ahead and just put a new line in there. I'm going to make this a little messy, and it might be a bit confusing, but hopefully if you pick it apart, you'll have a good understanding of what's going on here. And then I'm going to make a string, so cost table string, and I'm going to write a quick comprehension. So this might, I'm just going to go ahead and write it. Hopefully it's not too confusing. So I'm going to use an f string, and I'm going to make a list of these strings, and then I'm joining them all together to create the cost table. So so that's tab, and then I want to put the node in there, and then tab, and then I want to put the let's see, I want to put from the values, I want to put the cost, and notice I'm using double quotes there because single quotes will fail. And after I do that, that's the string I'm producing, right? And that's going to create multiple lines of this table that I'm making. And I'm going to say for node and vals in self.cost table.items. I'm using nodes and vals here in place of keys and values. And remember that for a node, the value is actually a dictionary, and that's why I'm saying vals subcost here. So I think that looks good. And I'm just going to return two things. Well, I'm going to return I'm going to return a few things, let's say. I'm going to return self.nodename, right? Because I want to talk about which node this actually is. And I'm going to put a line break there. And this is what I was saying. It's going to look a little messy, but it's going to get the job done. And I think it'll look nice when it's output. So, and then I want to look at the connections, and I'll say self.connections, and these are all the immediate connections to the current node. And then I'm just going to put in the cost table. So I'm going to put something on the end of that, and I think here, let's see, before and after, yeah, okay, this works. I'm going to put the cost table header, and if you recall, that has a line break in it, so I don't need to worry about that. Put in the cost table header, and I'm going to put in the cost table string. So that looks like a big mess, I know. And I'll commit this right away if you're following along and you don't want to try to recreate this from looking at a screen. You can grab it from the repo. I'm actually just going to take the same thing and use it for the dunder str method. And the reason I'm doing this is that, okay, well, we've got a node that we're making here, but we're actually going to make a graph, and a graph is going to be composed of nodes. So when I output the graph, I'm going to want to see all the nodes. So, and we'll get to that in just a second. All right, so let's see if this runs. Python Dijkstras. Cool. So that's promising, although we do seem to be missing something. We seem to be missing the previous node here, right? So we've got the node, we've got the cost, and we've got previous. Obviously, since this is node name A, this is node A, these are the connections. The cost to go from A to itself is 0, and the previous is none. So that's what we're seeing. And I think that's where I want to leave it. Let me think about this. It might make sense to put, well, I think I am. Oh, it is my intention, actually, here. Ah, okay. So for name, cost, yeah, for some reason I'm not seeing the previous node populating. Let me see what I'm missing here. For name, cost, and self.connections.items, self.cost table subname gets the cost as the cost, and previous as self.node name. Huh. Yeah, I'm not sure why. Why I'm not getting those previous. Huh. So let me I'll just output the cost table self.cost table, yeah. Cost table. Let me just take a look at that, see what's going on here. Yeah, okay. There's something wrong with my dunder, repr and dunder string. Okay, so vow's cost. Ah, I'm missing the. Yeah, I should have another tab in here, and this should be vowels sub previous. I think that's what's going on there, and I'm just going to copy this and also put this under my dunder string, and hopefully that will fix what we're seeing there. And I don't want to print the cost table anymore. I want to print just the representation of A, and that's what dunder repr is. It's repr is representation. Okay. Invalid syntax. Self cost table not items. Let's see. Yes, the joys of live coding. I see it. These should be double quotes. Otherwise, I'd have to escape them because we're in a string. So, oh, that didn't seem to be it. For string, I only changed it in one. I need to change it in Dunder Repr as well. Okay. It's not a bad getting stuck. Okay, there we go. And this makes more sense, right? So there is no previous for node A. We're just, because we're assuming A is going to be our starting point. And our cost table is going to connect to every other node and show the cost from each node to A. But so far, because we haven't implemented any sort of algorithm to traverse the entire graph, and we haven't even really written a graph yet, we're starting at A, and we can only see the costs to B, C, and D. And we see the previous node here. Awesome. So that's probably as far as we want to get offhand with Node for the moment. But what we're going to do ultimately is, we're going to write a function, write a method that builds the cost table. And I'm just going to put in a stub for this called build cost table, and obviously referencing self, and we're going to pass in a graph. And we're going to start writing that shortly. So this is going to be its own class, and we're going to want to initialize a graph and then populate it with some nodes. And this may seem like, well, why aren't we just doing this all within a graph class? And my answer to that offhand is I want to imagine a world where there are multiple graphs and a single node can actually belong to a different graph as well as the current graph. So we might be looking at A in light of this shipping network or this set of bike trails, but maybe A is also part of a different shipping network and different set of bike trails, and for that reason we might want to keep the concept of a graph separate. Like we might want to use multiple graphs, and we probably ultimately want to build in the flexibility to add more nodes to a graph, as well as add more connections to a node and rebuild our cost tables kind of dynamically as we go. Now, just to be clear, Dijkstra is sort of like set and go kind of algorithm. You build the costs and your cost table, and that's sort of like a static assumption. It's meant to apply to a closed network in general. There are other shortest path algorithms if you don't know, if you have an open-ended network, let's say, like routers, for instance, don't use Dijkstra's explicitly. They use a different shortest path algorithm. I don't remember which one offhand. They probably use a number of different ones. But they hold some kind of state as a node, like the router holds some sort of state and some kind of cost table that can be updated based on something like a router going down. It can back populate the values in the cost tables of various routers. And that's part of my logic here with having the cost tables not live in the graph, but having them live in the node. And so each node will have its own cost table. And when you ask for the distance between two nodes, you're actually asking the from node the distance to a to node. And there are some other smaller philosophical things in here that I might bring up later. You know, there's sort of like a fault that I'm writing into this that I think is a helpful construct. Okay, so I'm just putting this little stub in here, and we're going to come back and look at that. So when I build my graph, I'm going to do this fairly simply. I'm going to say graph gets graph, and of course we haven't defined this yet, so we're going to go back and define it. And we're going to do graph dot. We're going to write a method to add nodes, and for now we're just going to add a, because that's all we really need at the moment. Oop. Okay, there we go. So up here, I'm going to say class graph. Oh, you know what? I should commit really quick. I'm going to commit some broken code, but hey, at least the cost table is working if you're trying to follow along. So I'm going to just commit. I'll add that file, git commit, and I'll say working cost table. And I'm going to just push that, and that should be good. Okay. All right, so we've got this graph that we're going to go ahead and fill in. And as we saw in the node class, we're going to make an init method. And that's just going to reference self. I'm not actually going to pass anything in. We could, you know, why don't we do that actually? I'm going to add a nodes in graph and default this to an empty list. And I'm going to say self.nodes in graph is going to get nodes in graph. So, you know, by default, if we just call the graph constructor as we did before, like graph gets graph with open parens, really what we're seeing is defaulting this nodes in graph class variable to an empty list. So if we were to use init and pass something in, we could explicitly pass in a. But you know, I want us to have the option of making an empty graph, just because. Okay. And so the method that we use down here is graph.addNodes, and we're going to want to write that. But let's make that dependent on another method called addNode, and that's going to just take a node. And this should seem pretty boneheaded, pretty simple. We're just going to append the node to this nodes in graph. Now, you might be wondering why I'm using a list and not a set. And I don't have a good answer for that. You know, I think the expectation is that a graph is only going to have a single instance of the same node. So there's a fault. There's another fault I'm actually writing into this, is the ability to add the same node multiple times in the graph list, which is shouldn't actually lead to errors. I can't think of how it would, but it might actually make more sense to use a set for the nodes in the graph. But I'm not going to. It would be easy enough to change. This is just my preference, you know, given the way that I'm writing this. So we're just going to go ahead with this. All right, self.nodes in graph.append node, and then we want to add multiple nodes potentially, and this is going to be a node list. which is not a class that I'm writing or anything, but it's just going to be a list of our nodes. So remember, a list can hold anything, right? And we're going to pass in a list of objects, and those are going to be node objects. Objects, being the things that we use, the things that we create from a class. So we're going to add nodes. I'm going to say for node in node list, and I'm going to use this method above, self.addNode, and I'll just add the node. So that should be pretty clear cut, right? Add node, self, comma node, self.nodes in graph.append node, right? So this is going to, if we had a single node, append it to the nodes in the graph. And if there are multiple nodes in a list, we're just going to call this over and over again and pass in each node in that list. So I might be wrong about this, but I think we can go ahead and look at our graph. Well, look at it in the sense of output it in a way that's meaningful. I might be wrong about that. We'll find out. So graph.addNodes, and why don't I just print the graph? And this is going back to using the dunder repr, unless I'm forgetting something. I might be, but we'll find out. Ah, I must be forgetting something. So let's think about that for a second. Oh, I know what I can do. I can do this. Nodes in graph. Right. This should be our list of nodes. And if I output this, then we see node name A. So that said, why don't we go ahead and make some more nodes and see how this changes. So I've got A here. Here, I'll go ahead and commit Dijkstra's, and I'm going to commit and say create graph class, and I'm going to push. So if you're following along, that diff should be associated with that commit. All right, so we made A. Let's go ahead and make B. And this is going to be a little tedious, but I'll do a couple of these, and then and we'll look at the change in output, and then I'll go ahead and just finish up the rest of them really quickly. So node B, B should be named B, not C. So it connects to A with a cost of 5, and it connects to E with a cost of 4. All right. And yeah, sorry about any ambient noise. There's home repairs happening next door. So let me go ahead and run this, and I think we should see what we're seeing here, right? We've got node name A, the connections from node A, node name B, and the connections from node B, and the cost tables for each of those. And when we're thinking about this, consider that each of these tables is working, each node is assuming that it is the home node from which you're traveling. So when we're looking at this cost table, we're looking, as we populate this with all the other nodes, all 8 of them, we're going to be, if we're looking at node name B, we're considering that the home node, and all the costs are going to be relative to traveling from B. So hopefully that's clarifying. And I'm just going to go ahead and type the rest of these in. I'll go ahead and copy paste these. So B, C, D, E, F, G, H, and C, D, E, F, G, H, there's a really good chance I'm going to make a mistake in here because I'm doing this manually, but if you are paying attention and you see me make a mistake, please tell me and I will correct it. Okay, so B is done. Let's look at C. C goes from, it has a cost of 7 from A, and it's connected to D with a cost of 3, and it's connected to F with a cost of 5. And then go ahead and delete that. And D is connected to A with a cost of 2. It's connected to C, with a cost of, see, this is D, connected to C with a cost of 3, and connected to E with a cost of 4. I already have that there, right? D is connected to E with a cost of 4, and it's connected to G with a cost of 6. We're almost there. All right, so E is connected to B. Nope. Connected to B with a cost of 4. It's connected to D with a cost of, let's see, this is E, let's see, B with a cost of 4, D with a cost of 4. Yep. And G with a cost of 2. And F, oh gosh, we're almost there. All right, C with a cost of 5, G with a cost of 7, and H with a cost of 6. And we've only got 2 more, so G is connected to D with a cost of 6, E with a cost of 2, and F, oops, with a cost of 7, and H with a cost of 3. All right, and then the last one, H is connected to F with a cost of 6, and connected to G with a cost of 3. All right, so I'm just going to take a quick double check of this. AE54, C is ADF735, D is ACEG2346, ACEG2346, E is BDG442, C5, G7, H6, D6, E2, F7, H3, F6, G3. Oof. Yeah, that may have been a little bit tedious. Sorry about that. But you know, gotta get those right. And then, you know, we'll just throw all of these in the in our add nodes. So G and H, and if I run these, we get output of these cost tables, these initialized cost tables. And yeah, they all kind of give a similar sense of being kind of incomplete, but we're going to complete them. So just do that. All right, so let's go ahead and add the file, git commit, and we'll say, you know, create all nodes in graph, and let's go ahead and push that. Cool. So at this point, I think we're able to start coding Dijkstras, and my hope is that the there's a couple functions here that we're going to code. We're going to code the building of the cost table, and then we're going to code getting the shortest path. So let's just kind of define what's happening with Dijkstras here. And I'm not going to do a proper docstring, but I want to just give an idea of what Dijkstras is doing. So the initial thing we do is we, remember I am borrowing this framing of the algorithm from that computer science video that I linked to in the description. The channel is actually called Computer Science, but this is a widely used algorithm, and I changed a few of the words. I think he uses vertex, I use node, and I added a couple of steps in here, but it's essentially the same algorithm. So I'm going to let the cost from a given node, this node, right, from this node to itself equal 0, which we already did, right? We can see that in the cost table. Now just, if you want to take a look at that cost table. Let's see, Python, there we go. Get a little representation of it there. Let the cost from this node to itself equal 0. I'm going to populate the cost table entries with all nodes in the graph, and that step you're going to see is going to involve actually passing the graph into the function itself. So we're going to let the distance to all other nodes equal, I'm going to go with 10 to the 9th, which is going to be our representation of infinity. We're assuming that we're never going to have a cost that's actually that high. All right, so that's our initialization of the algorithm. And oh, somebody's mentioning that they can't see the top half of the terminal. I'll go ahead and remove the graph. Good point. Sorry about that. Just turn that off. All right. Okay. Let's go ahead and continue forward. All right. So once we have that initialization, we're going to commit the algorithm itself. And this is sort of light algorithmic language. We do a repeat kind of until, and you can think about that as some kind of loopage, some kind of for loop. So we're going to visit the unvisited node with the smallest known distance from this start node. And with that, we're going to say for the current node, that is the current node, the unvisited node with the smallest known distance. So for the current node, we're going to examine its unvisited neighbors. So if its neighbors have been visited, we don't want to look at them. And we're going to say for that current node, we're going to calculate the distance of each neighbor from this start node. Right, from this start node, from this. This start node is not the current node, mind you. It's the node itself for which we're building the cost table. And then, our very light logic in here is going to be, well, if the calculated distance of a node is less than the current distance in the cost table, we're going to go ahead and update the shortest distance in the cost table. And this is where we're not going to modify the immediately adjacent nodes, right? That wouldn't make any sense. We're going to modify things if there's a better, quicker way to get there. And then we're going to say update the previous node, right? So if we modify that shortest distance, we're probably going, well, we're definitely going to modify the previous node as well, the entry for previous node. So update the previous node for each updated, let's say updated distance. Yep. And then we want to add the current node to the list of visited nodes and remove it from the list of unvisited nodes. And we're going to do that until all nodes are visited. So that's our basic algorithm. I'm going to just, throw that into Git really quick so that you can take a look at it if you want to read through it, because I'm going to be jumping around and actually coding this very shortly. So let's say git commit, add description of Dijkstra's, and we'll push. Cool. All right. So notice I mentioned this visited and unvisited. Technically, we only need one of these, visited or one unvisited. But I'm going to go ahead and do both because it's kind of a convention. Every implementation I see of Dijkstra's has a visited list and an unvisited list. And, I just want to stick a little bit to convention. I actually deviate from this algorithm slightly. So these initializations, these have already happened, right? Let the cost from this node to itself be 0, populate the cost table entries. Well, I haven't done that. Okay, so I've just done this initial thing. And when we look at this, one of the things we can do, let me just jump back over to VS Code. We can say that we've already visited the self, right? We visited this node already because we already initialized it. So I'm going to go ahead and start the visited list with the self.node name, which we don't actually have to use the node itself. We can use the name of the node, and we're going to pass that name around quite a bit. So the first thing we're going to do is we're going to populate the cost table entries with all nodes in the graph. Note that we already populated the other nodes, the connection nodes. So let's just say with the remaining nodes in the graph. And when we do that, we're going to let the distance to all other nodes equal 10 to the 9. And this is a stand-in for infinity. So this is where it gets a little bit messy. Notice up here, we've passed in a graph when we define this. So when we call this, we're assuming that we have a graph available. And I'm going to say, for node in graph, and these are actual nodes. These are the node objects. So I'm just going to call it nodes in graph. And remember, that's our, this is our primary class field up here, right? Self.nodes in graph gets nodes in graph. So when we build this, when we added our nodes, this should have A through H in it. So let me just go back down here for node in graph, nodes in graph, and we're going to go ahead and say if the node.node name is not in self.cost table, as in we have not added it to the cost table. So this will exclude the self name, and it'll exclude the the immediately adjacent nodes. So if node.nodename not in self.cost table, we're going to update the cost table, and we're going to say cost table subnode dot node name, right? Node name is a field of a node, and so we can use that. I'm going to say self.cost table subnode name, and that's going to get that same dictionary that we saw before. So where the cost is, by default, we're setting this to 10 to the 9th, and we're setting the previous. We're assuming that we don't know the previous yet, the previous node. So we're going to just set that to none, and that should do actually. So why don't we build A down here, right? Let's go ahead and, we've established A. Instead of, why don't I print, I'll do both. I'll print A first. So I'll print A. And we should see, barring any code errors, which there probably are some, we should see a populated but not completed cost table. Oh, that does not look like it is working. Cool. Okay, so let me track down what I'm missing here. So self.cost table, node.nodename gets cost 10 to the 99. Am I doing this? Okay, I add the nodes, then I print A. Oh, of course. I am not actually calling build cost table. There we go. And I want to pass in the graph. That's what I was missing. And I think this should work now. And it does. Cool. So A, B, C, D, E, F, G, H, all of our nodes are present. We have the cost to the adjacent nodes and the previous for the adjacent nodes, but notice we've got this massive number for the cost to E, F, G, and H, and their previouses are none, but we're going to do something about that. So I think we should have a decent representation of all the nodes if I go ahead and print the entire graph. And but we haven't actually run the build cost table method. So that's something that we're going to need to do. And we want to think about when and how to do that. So, let's say we add the nodes. We want to make a method in graph to build all the cost tables. So why don't I just commit this and call this populate cost tables, and we'll push that. So that should be in a good spot. And let's go ahead and write a method in the graph where we build all the cost tables. So notice that we can have a graph, and we can add a node to it, and then we can build the cost table again. So that gives us a bit of dynamism, So why don't we write this method called build cost tables, and this is going to operate on all the nodes in the graph. We're assuming that we want to do that, and we're going to say for node in self.nodes in graph, and we're just going to, node.build cost table and of self. So that should work. And down here, where I haven't yet built the cost table, I can go ahead and say graph.build cost tables, and that should be fine. And it looks like that's working. So notice all the nodes are built, all their cost tables are built, but they're not yet populated. So instead of writing out all my commit, I'm going to use a function that I wrote, a little bash function called getAdder, and I'll just do add build all cost tables. So that'll do what we want it to do. So let's get back to Dijkstra's algorithm. All right. So that was our initialization. And, in general, I wouldn't write this many comments, but I want, to make this educational. So let's populate the unvisited list with all the node names. And that's going to be fairly easy. I'm going to write a quick comprehension for this. I'm just going to say unvisited is going to get node.nodename for node in graph.nodes in graph, right? That's all of our nodes. And if the node.nodename does not equal this particular node's node name. Okay. So that should be pretty straightforward. I'll just go ahead and run this. Make sure nothing's amiss. And I'll say populate unvisited, and we'll go from there. All right, so next in Dijkstra's algorithm, we're going to perform some loopage. And one of the things to consider here is we don't actually know how many loops we're going to perform. And though that seems like a great case for a while loop, I avoid while loops, and I'm not recommending that you avoid while loops. I'm just saying I do, and I build in some kind of, de facto fault tolerance by using a for loop. So I'm going to say for, well, first let me say what we're doing here. So I'm going to say, instead of using a while loop, let's assume a max of, I'm just going to say n nodes, capital N nodes in unvisited, and create an exit condition. And what we're actually doing is if a cost, so we're going to step through the nodes, prioritizing the lowest cost paths, or maybe I'll say lowest cost nodes, and updating the cost table accordingly. All right, so this is the real part of the algorithm right here that we're going to write. I'm going to say for whatever in range, I'm going to assume for now that we're not going to have more than 100 iterations of this loop. So I'm going to search for the node with the lowest cost. And I'm going to do this with a quick comprehension and using the min method, min function. And what I want is the min cost and the min node. And I'm going to get that out of, let's look at the cost table in its current form. Self.cost table sub node name. And we're going to look at the costs. I'm actually going to build a tuple here. And then I'm going to sort the tuple. So it's going to have the cost, and then it's also going to have the node name itself. So, and I'm going to say for node name in the unvisited, right? Because I only care about looking in the unvisited for the lowest cost node, next node. That said, I want the minimum cost, right? And notice that the first value in this tuple is the cost, and that is how this is going to sort. So I'm going to grab the minimum value from that. That's going to go get unpacked into the min cost variable, and the node affiliated with that cost is going to go into the min node variable. So that should work. And now that we know the name of the min node, we actually want to get the node itself. So I'm going to say min node is going to, we're going to get this from a method that I write on graph. Now this method doesn't exist yet, and I'm going to write it right now. So we're going to go up to graph, and notice we build our cost tables. We're adding nodes. We also want to get a node, and that's going to be self, and I think we want to just call that node. And this should be fairly straightforward, right? We're just getting this out of self nodes in graph. So we'll do this with some loopage. There's, it's not that there isn't a better way of doing this, but just given the nature of this in its current form, this is a way to go. Something that might make this faster is if I had a reference, like a dictionary reference, where I could look up the node name, and that would point me at the index for where that node lives in the list of nodes. And that would be a slightly more optimized version of events. But we're not assuming massive graphs here, so I don't think we're going to hit any kind of performance lag. So if the node name, so for node in self.nodes in graph, if node.nodename equals node name. Oh, yeah. No, that's fine, because this should be not node, but node name. So this is only the name, and we're referencing this. We're saying if that is, if those are equivalent, then we actually just want to return that node. That's going to end our function right there. We're not making this bulletproof, right? Like if you were to look for, this would return none in the event that the node name is not in there, which would crash our network, but that's okay. We're not too worried about that at the moment. So we can go back down to here, and min node gets graph.getNode of min node. And so this is going to be the node itself, min node, and that means we have access to the adjacent nodes and the costs from that object. And that's what we want. So what's our next step? We want to calculate the cost next. And that's going to be pretty easy. And we only want to calculate the costs for each of the adjacent nodes. And we're not going to do that in any particular order. We're just going to do it by the order that is set in the adjacent nodes. So I'm going to say, how do we want to do this? So we want to do the node name for node name and the cost in that minimum nodes connections. Remember, that's a dictionary, dot items. So this is the key, node name, and the value is cost. We're going to say the distance from the starting node. I'm just going to say start. The distance from start is going to be the min cost plus the cost. And we're going to see if this is less than what we already have in our table. That's pretty straightforward, that logic. It might look a little confusing. I'll talk through it. If the distance from the start is less than the value that's in the cost table, so this is cost table sub node name, right? This is available to us. Sub cost, right? That's the cost affiliated with that node name. If this is less, right? If our calculated distance is less than what we see in the table, then we're going to update the table. We're going to update the table with let's see, cost table sub node name sub cost is going to just get the distance from the start. And if we do that, we also have to update the previous, right? So currently all these previous values are set to none, but we're going to change that. And we're going to say self.costTable sub node name sub previous, right, is going to get the node name of the minimum node. And that's pretty much it. That's pretty much our entire algorithm. And you know, we do have to do a couple cleanup operations here. We need to add things to visited and remove things from unvisited. So that's pretty straightforward. Let's see. So within our for loop, I'm just going to say, well, if we visited it, I'm going to append it to visited. So this is min node dot node name, and if that node name min node dot node name is in unvisited, we want to remove it. And you might be asking why I'm putting this condition in there. It's because on the final loop of this, we're actually going to, on the final loop for a given node, right, we're going to take this node and we're going to end up trying to check it when it's already been removed. So let's just avoid that with this if min node name in unvisited. And like I said, you don't really need a visited and unvisited, because notice I'm performing two operations here when I could just perform one. I could just qualify things against visited, but the convention that I've seen is having a visited nodes and an unvisited nodes. And I'm not entirely sure why that is, but I just want to stay a little bit true to the algorithm that I've learned in the way that I've learned it. So I'm just going to remove that node name from unvisited, which means we're not going to check it again. And after we do that, let's see. Let me make sure that I'm So we're in this inner for loop right here. And what we want to consider is once this is our exit condition, this is what you might see in a while true loop, or you would see this in the condition for a while loop. But I like to prevent infinite loops just in case when I'm coding things, and I don't. I mean, maybe somebody can chime in on this. Maybe there's a reason to use while loops sometimes, but I just think you can kind of always use a for loop and have it be totally fine. But if unvisited has a length of 0, we can break because we're done. So that's kind of it. If I run this, barring any errors, which, you know, looking at this wall of code, we're probably going to see some errors. If I run this, I think we're going to see populated cost tables. So, oh, min nodes is not defined. Where is that line? 80. Min node, not min nodes. That's easy. I should have seen that. And let's try that again. Oh my gosh, and it works. So this is kind of a wild thing. This is not a very complex algorithm. And if you pick it apart, you'll see how, you'll see some utility in it. We could put in hundreds of nodes. I'm not going to force you all through that. But, you could do something like write a random node generator, right? And, have an update to the nodes so that you build, you make this, massive, highly interconnected network where, you get a shortest path. So, we'll take a look at how this works in a second. Yeah, well, let's just take a look at it now. You know what, let me commit. And so git adder, finish Dijkstra's, and I'll go ahead and run this again, and we'll take a look at it. So let's look at connection A, and let's see if this is telling us the truth. So I'm going to pull up that image of the graph again, which I think should be helpful here. And after that, we'll write a function that'll just get us the shortest path and get us the cost for that shortest path. Okay. All right, so let's take a look. So starting at let's say we're trying to go to H. If we look at this, we're starting at A, and we're going to H. So there should be a cost of 11. If we look at H, well, what is the previous to H? It's G. And then we look at G. What is the previous to G? It is D, right there. And we look at D. What is the previous to D? That is A. And it turns out that this is the shortest path, A to D to G to H. That has a cost of 11. If we look at all these other costs, for traversing this graph, we're going to see all of them are higher, right? Like if we went around like this, it would be 5, 9, 11, 14, or if we went this way, it would be 12, 18. So yeah, this algorithm is working, and it's not a complex algorithm, but it does take a little bit of finagling. I don't know. It takes some thought and playing around with it. So there are some little things that I want you to consider here. Since each node carries its own state, we actually can make graphs that have different costs on the same path. And I'm not going to demonstrate this because I want to show, just write the function for getting the shortest path. But this is something to consider and something you might want to play around with. This code's all up on the GitHub, and you can get a sense of what's going on here. So let's say we're traveling from D to E, and in one direction, this is 4 from D to E. But then in the other direction, this is 6. That's something to consider. And the way that we coded this, it shouldn't have a high impact in terms of breaking Dijkstra's algorithm. But there are cases where it might. The other thing to consider is, let's say you have a negative path cost. What do you do then? That's kind of a weird one. What if you have -6? It's possible. And you might see this as, well, if maybe there's a cost incentive for delivering through a certain distributor and they're giving you a kickback. So, because of that cost incentive, it makes more sense to actually go add another node because you're taking 6 off. So those are things to play around with. Some of those things will actually break this implementation of Dijkstra's, and you'd have to modify a little bit in order to avoid that breakage. But in general, this is Dijkstra's algorithm, and the only thing left is to code out a getShortestPath function, and I believe that'll be it. So we're going to do that within the node class. We could also double this. We could also call this from a graph, from the graph. So I'll code this. Is that the level we're at? That looks right. Nope, one level in. Okay. Let me just get us back there. I'll code it up here. It's a nice short one, so it's actually kind of a not very nice looking short one, but it's fun. I think the logic here is kind of cool. I'm sure there are better ways to do this. If you have a better way to do it, definitely post in my issues on GitHub, and I'll put in an alternative. I just think this is kind of a neat way to do it. So let's get the shortest path to something, and we'll say self and some node name, and I'm just going to start this off with a shortest path list, and I'm going to populate this list. I'm also going to populate a list of the costs, and it may not be obvious, but in our cost tables we have all the costs in there. We just have to perform subtraction to get them out. I could grab them in a more explicit way that would be much more complicated, but I'm not going to. I think this is a nice, elegant way to get the costs. So the total cost, we have this, right? That's just from the cost table. So this is self.cost table and some node name and the cost, right? So we know that. And I'm going to start off, since we're considering some node name and we're kind of working from our, oh, you know what? I am coding with that document camera in front of everything. My apologies. I was talking about this getShortestPath function. Self, some node name, shortest path. That's where we put our nodes in the path in reverse order, the costs affiliated with those nodes, and the total cost gets the self.cost table of some node name subcost, right? Because that is our total cost that we see in the cost table. Great. Let's continue forward. I'm going to have a sort of working variable here that I'll use, and I'm just going to call that current node. And I'm going to put in some node name, just a copy of the name itself, so that I'm not modifying the parameter here. I just want to use the value that's in it, and I'm going to update that value. So I'm making a new variable to hold that. And I could use a while loop here because we don't know how many nodes we're going to use, but instead I'm going to do that weird thing that I do with a for loop, and I'm just going to say for whatever in range, we're going to assume not more than 100, although later I'll change these to 10,000. I think no one's going to be using this for 10,000 nodes. Maybe. I don't know. So we're going to append to the shortest path the current node, right, which is the node that we passed in. And we're going to say, well, if the current node, if its previous is not equal to none, right? So if we haven't arrived at the root node from which we're traveling, then we're going to say, we're going to append the cost, which is, this is just really simple. It's the, from the cost table, we're going to take the cost from the current node, and we're going to subtract from it the cost of the previous node. So self.cost table, and this is going to be messy, but it's a little trick. I'm just going to say self.cost table sub current node sub previous. You know, so I'm referencing this in a not a very pretty way, but it does get us what we need to know. And this is just a simple subtraction. It's you know, the cost, the current cost, and the cost of the from the previous. And you know, if you look at the graph itself, if we kind of take just a quick second peek at this, you know, the total cost from A to H is 11, and what we can do once we have 11, we can do well, we can do 11 minus 6 minus 2, right, and that'll get us 3. And we'll see if that actually works. I think it will. Okay. All right. So the other thing, we need to update our current node, right? Because we're changing this. So current node, and this is just going to take the previous. So self.cost table sub current node sub previous, and then we're going to break if the current node is none. So that's our exit condition for this for loop, and you know, we're going to hit that, right? We're going to hit that at the point where we're at the root node. And you know, there's a little more to this. So I'm going to take the costs, and I'm actually going to do this with both the costs and the nodes. We're going to want to reverse them, but I also want to give some kind of meaningful output in the form of a string. So the first thing I'm going to do is convert all of these cost values to string values, right? So string of cost for cost in costs, and then I'm going to reverse this, and that's going to give me a reversed object, so I'll just cast that to a list. This isn't the only way to reverse something. List reversed is a little clunky, but you know, it's what I'm doing here, and it's what I tend to do, although it makes more sense to do indexing to reverse a list, just because why make a reversed object and then cast it to a list? Great question. At the end of the day, I think this is slightly slower, but not, you know, we're not going to be doing it that much, so I think it's fine. So I'm going to go ahead and make a return string, and this is going to be really pretty, sort of, not really. I'm going to make something that gives us a sense of the path and embeds the cost in the path. So I'm going to enumerate the reversed version of shortest path, and this is actually a better use of reversed because it's an iterable. I'm going to say if the index is less than the length of the costs, then I'm going to append some text to the return string. So I'm going to take the letter, right? That's the node letter, and I'm going to just go ahead and interpolate the associated cost. And I'm going to make that an arrow, I guess. Why not? And oh, that's extra. Okay, so is that right? Yes. And otherwise, at the end of our path that we're displaying, we just want to append the letter. We don't need an arrow at the end. So I'll just do that. And maybe I'll also append onto this the total cost. And let's see, total cost. And we've got that above. We got that first thing. And I believe we can just return that return string. So let's see if this works. I'm going to get the shortest path from A to some node name. That should say costs up there. And okay, I think we're good. So I'm just going to call this down here. We'll build all the cost tables, and then I'm going to say I'm going to print a dot get, what is it? Get shortest path. Seems like that's what it should be called, get shortest path. Let's find that. Get shortest path 2. Okay. Oh, filled it in. All right, and let's get the shortest path to H. Our expectation there is that it will be the 11, and it will have interpolated into it the path values themselves. Let's see. Oh, line 47, node name H. Let's see. Interesting. I wonder what's happening there. Well, let's look at line 47 and see what's happening. Total cost gets self.cost table, some node name gets the cost. Huh. H should be in the cost table. Not sure what's happening there. Yes, the joys of live coding. Let's Let's just see. It's done. Let's try that. All right. Interesting. Okay. Get shortest path to H. Oh, wow. Okay. It's the node name, not the node itself. Okay, so that makes sense. And yeah, let's just bring up the graph itself just to verify what's going on here. We start at A, we go to D, that has a cost of 2, and we go from D to G, and that has a cost of 6, and we go from G to H, and that has a cost of 3. So this is a, a functional implementation of Dijkstra's algorithm. Could definitely build this out more. There's other things you could do. One of the recommendations I have is, write a get shortest path function for the actual graph, right? That would be, well, why don't we just do that? I'll do that, and then we'll call it. So this is going to be very easy, I think. Let me just, I'm saying that, but we'll find out. Get shortest path, and we're going to have a from node. Well, we have to reference self, and then we have a from node and a to node. And we want to get a node, and we want to, yeah, I think this works. Okay, so our from node, why don't we call this from node name? And to node name. And we'll say from node is going to get node of, well, this is self.getNode, right? Self.getNode of the from node name. And then we're going to return the from node dot get shortest path to, I believe. Get shortest path to of the to node name. So let's test that out. And let me do that one more time. I'll go ahead and talk back through that since I covered it up. And so we're going to define get shortest path, and this is in graph, right? From node name to node name. And notice those are node names, not nodes. So we actually want the node, and we're going to just use this get node function from that node name. And then we can just return from node.get shortest path to get shortest. Okay. Get shortest path to. the to node name. So that should work. And this kind of gets things a little more flexible, right? You can ask the shortest path from any node to any node without referencing a node in particular. So why don't we go ahead and do print graph.get. That's probably going to give us get node, isn't it? Yep. Get shortest path is what we want. Shortest path. And we want to go from A, we'll just do A to H again. And I think that will work. Let's find out. And it does. Awesome. So I'll make my final commit here, and I might update this code a bit. If you have any suggestions, feel free to throw them in the comments. I might, build this out a little further. Create some different branches of it. We'll see. There, might make sense to build a different shortest path algorithm instead of Dijkstra's and add that in as well. Feel free to extend this in any way you want, fork the repo, use this to solve an actual problem. I was thinking it might be cool to take a bunch of current research papers from the last, let's say, 2 years off of archive.org and consider a connection to be, a paper shares an author with another paper, and consider the cost to be, let's say, consider the cost to be something to the effect of the similarity between the term frequency matrix of one article and another article. And if you consider the article to be a node and its connections to be the authors and the cost to be the similarity, you might look for the most similar path, right? So the lowest cost path between two articles. And there may be some articles that are unreachable given the kind of matrix of, given the network of published articles. But I think you might have some surprising results if you use a network like this in that kind of task. Maybe I'll do that, but I probably won't do it for this channel. It's a little bit out of the scope or above the skill level of most of the people watching. So be a fun experiment either way. So let's see, are there other things that you could write into this? Yeah, generating a random graph, I think, is something that would be very worthwhile, right? I'm hard coding a graph here, but you can imagine that there are times where you would want to generate a random graph. And I will go ahead and say Dijkstra working and MVP done. I'll just say that. All right, thanks so much. My name is Tovio Roberts, and I work with the Galvanize Data Science Immersive. Yeah, I'm going to try to keep this up on Thursdays, generally have a coding session and work on something that is not just coding, but coding where we're tackling a concept, exploring a concept. I'm considering next week maybe doing some simple generative music, generative beats. That's something that I've been playing around with, and there's a really convenient library for that. So if you have any suggestions on things you'd like me to cover that are sort of in the elementary scope of data science and computer science for people learning to program and solve problems with code, drop a comment and I will take it into consideration for sure. All right. Thanks so much and have a wonderful day.